Resistance is a measure of the opposition to current flow in a material. Impedance is a measure of the opposition to current flow in a circuit, which includes resistance, inductance, and capacitance. The resistance of Earth is not negligible, but it is very low. The Earth's resistance varies depending on the soil conditions, moisture content, and temperature. The resistance of Earth can be as low as 1 ohm or as high as 100 ohms. The impedance of an earth electrode is the resistance of the electrode plus the resistance of the earth in contact with the electrode. The impedance of an earth electrode can be as low as 1 ohm or as high as 100 ohms. The impedance of an earth electrode is important because it affects the amount of current that can flow through the electrode. The lower the impedance, the more current that can flow through the electrode. In the case of single-wire earth return systems, the impedance of the grounding electrode is important because it affects the amount of current that can flow through the earth. The lower the impedance, the more current that can flow through the earth and the more effective the single-wire earth return system will be. When discussing grounding and earth resistance, it's crucial to understand the fundamental concepts and factors that influence these parameters. Let's delve deeper into each aspect. Firstly, resistance, in the context of electrical circuits, quantifies how much a material opposes the flow of electric current. It is measured in ohms. A higher resistance means a greater opposition to current flow, while a lower resistance facilitates easier current flow. Secondly, impedance is a more comprehensive measure than resistance. It represents the total opposition to current flow in an alternating current AC circuit. Impedance encompasses resistance, but it also incorporates the effects of inductance and capacitance, which are frequency dependent. Inductance arises from the presence of magnetic fields created by current-carrying conductors, while capacitance stems from the ability of a component to store electrical energy. Therefore, impedance provides a more complete picture of how a circuit behaves under AC conditions. Now, addressing the specific case of earth resistance, it's a common misconception that the Earth's resistance is negligible or practically zero. While it's true that the Earth is a vast conductor, its resistance is not insignificant. Several factors influence Earth resistance, including soil composition, moisture content, temperature, and the presence of dissolved salts. Soil composition plays a significant role because different types of soil have varying electrical conductivities. For example, clay soils generally have lower resistance than sandy soils due to the higher concentration of conductive minerals and moisture retention. Moisture content is another critical factor. Water is a good conductor of electricity, so the presence of moisture in the soil significantly reduces its resistance. Conversely, dry soil exhibits much higher resistance. Temperature also affects earth resistance. As temperature increases, the movement of ions within the soil increases, leading to lower resistance. The presence of dissolved salts in the soil can also lower resistance by providing more charge carriers. The resistance of earth can vary widely, typically ranging from 1 ohm to 100 ohms, or even higher in extremely dry or rocky conditions. It's important to note that these values are approximate and can change depending on the specific location and environmental conditions. When we talk about the impedance of a grounding electrode, we're referring to the total opposition to current flow from the electrode into the earth. This impedance consists of two main components. Firstly, the resistance of the electrode itself, which is usually very low, and secondly, the resistance of the earth in contact with the electrode, often referred to as the earth interface resistance. The earth interface resistance is the dominant factor in determining the overall impedance of the grounding electrode. It depends on the size and shape of the electrode, the depth at which it's buried, and the soil conditions surrounding the electrode. A larger electrode with greater surface area will have lower earth interface resistance compared to a smaller electrode. Similarly, burying the electrode deeper into the ground can reduce resistance by accessing more conductive soil layers. The impedance of a grounding electrode is crucial for ensuring the effective operation of electrical safety systems. A low impedance grounding electrode provides a low resistance path for fault currents to flow back to the source, allowing protective devices like circuit breakers and fuses to quickly interrupt the circuit and prevent electrical shocks or equipment damage. Conversely, a high-impedance grounding electrode can impede the flow of fault currents, delaying or preventing the operation of protective devices and increasing the risk of electrical hazards. In the context of single-wire earth return systems SWER, which are commonly used for long-distance power distribution in rural areas, the impedance of the grounding electrode plays a critical role. SWER systems utilize a single high-voltage conductor to transmit power over long distances, with the earth serving as the return path for the current. At the sending end of the line, a grounding electrode is used to inject current into the earth, while at the receiving end, another grounding electrode is used to extract the current back to the substation. The effectiveness of a SWER system depends heavily on maintaining low impedance grounding electrodes at both ends of the line. A low impedance allows for efficient current flow through the earth, minimizing voltage drop and power losses along the line. If the grounding electrode impedance is too high, it can significantly reduce the system's efficiency and reliability. In practice, SWER systems typically aim for grounding electrode resistances of 5 ohms or less to ensure proper operation. This often requires the use of multiple grounding electrodes connected in parallel or the implementation of soil treatment techniques to improve conductivity. While university researchers may report negligible earth resistance under ideal conditions, these findings are often based on theoretical models or small-scale experiments. In real-world applications, earth resistance is a significant factor that must be carefully considered in the design and installation of electrical systems, especially those involving grounding and earth return paths. To further illustrate the concepts discussed, let's consider some practical examples. Suppose you are installing a grounding electrode for a residential electrical system. To ensure adequate safety, it's essential to measure the grounding electrode resistance after installation. This can be done using a ground resistance tester, which applies a small current to the electrode and measures the resulting voltage drop. The resistance is then calculated using Ohm's law. If the measured resistance is higher than the recommended value, typically 25 ohms or less, you may need to improve the grounding system by adding additional electrodes or treating the soil with conductive materials. Another example is in the design of a large industrial facility. In such cases, a comprehensive grounding study is often conducted to analyze the soil conditions and determine the optimal grounding system configuration. This may involve using computer simulations to model the flow of fault currents through the earth and predict the performance of different grounding designs. The goal is to ensure that the grounding system can effectively handle large fault currents without creating dangerous voltage gradients or compromising equipment safety. In the design of SWER systems, engineers carefully consider the soil resistivity along the transmission line route. Soil resistivity is a measure of the Earth's resistance per unit length and is typically expressed in ohm meters. By measuring soil resistivity at various locations along the route, engineers can estimate the grounding electrode resistance that can be achieved at each end of the line. This information is then used to optimize the grounding system design and select appropriate electrode types and installation methods. In addition to the above examples, it's worth noting that various regulatory standards and codes provide guidance on grounding system design and installation. These standards, such as the National Electrical Code (NEC) in the United States, specify minimum requirements for grounding electrode size, material, and installation practices. Compliance with these standards is essential to ensure the safety and reliability of electrical systems. In conclusion, understanding earth resistance and grounding electrode impedance is crucial for anyone involved in the design, installation, or maintenance of electrical systems. While earth resistance is not negligible, it can be managed and minimized through proper grounding techniques. By carefully considering soil conditions, electrode design, and regulatory requirements, engineers can create effective grounding systems that protect people and equipment from electrical hazards. Now let's consider the practical implications of having a very low earth resistance. A very low earth resistance might seem desirable from a safety perspective, as it would provide a very low impedance path for fault currents. However, there are potential drawbacks to having extremely low earth resistance, particularly in residential or commercial settings. One concern is the potential for increased neutral current flow through the earth. In electrical systems, the neutral conductor is intended to carry the unbalanced current between the phases. However, if the earth resistance is very low, a portion of the neutral current may flow through the earth instead of the neutral conductor. This can lead to several problems. Firstly, it can cause nuisance tripping of ground fault circuit interrupters, GFCIs, or arc fault circuit interrupters, FCIs, as these devices are designed to detect small imbalances in current between the hot and neutral conductors. If a significant portion of the neutral current is flowing through the earth, it can create a false ground fault condition, causing the GFCI or FCI to trip unnecessarily. Secondly, neutral current flowing through the earth can create stray voltage potentials in the surrounding area. This can be a particular concern in agricultural settings, where stray voltages can affect livestock and potentially reduce milk production or cause other health problems. Thirdly, if the earth resistance is very low due to the presence of interconnected metallic objects, such as water pipes or gas pipes, there is a risk of creating circulating currents. These circulating currents can flow through the metallic objects and cause corrosion or other damage. To mitigate these potential problems, it's generally recommended to maintain a reasonable level of earth resistance, typically between 1 ohm and 25 ohms, depending on the application and local regulations. This can be achieved through proper grounding system design and installation practices. In some cases, it may be necessary to use isolation transformers or other techniques to prevent excessive neutral current from flowing through the earth. The discussion about single-wire earth return (SWER) systems is also relevant here. SWER systems rely on the earth as a return path for current, so the earth resistance plays a crucial role in their performance. However, SWER systems are typically used in rural areas where there are fewer interconnected metallic objects and less potential for stray voltage problems. In these cases, the benefits of using the earth as the return path, such as reduced infrastructure costs, outweigh the potential risks associated with low earth resistance. Furthermore, SWER systems are typically designed with careful attention to grounding electrode placement and soil conditions to minimize voltage drop and ensure safe operation. It's important to note that the ideal earth resistance for a given application depends on various factors, including the type of electrical system, the soil conditions, and the presence of nearby metallic objects. A qualified electrical engineer should be consulted to determine the appropriate grounding system design for each specific situation. The information presented here is intended for educational purposes only and should not be considered a substitute for professional advice. Now let's delve deeper into the methods used to measure earth resistance and impedance. Accurate measurement is crucial for verifying the effectiveness of a grounding system and ensuring compliance with safety regulations. The most common method for measuring earth resistance is the fall of potential method. This method involves driving two auxiliary ground rods into the earth at specific distances from the grounding electrode under test. A ground resistance tester is then used to apply a current between the grounding electrode and one of the auxiliary ground rods while measuring the voltage drop between the grounding electrode and the other auxiliary ground rod. The earth resistance is calculated using Ohm's law, dividing the voltage drop by the applied current. The fall of potential method requires careful placement of the auxiliary ground rods to avoid errors due to overlapping zones of influence. The distance between the auxiliary ground rods and the grounding electrode should be sufficient to ensure that the voltage measurement is not affected by the presence of the other ground rods. There are also variations of the fall of potential method, such as the 3-point method and the 4-point method, which use different configurations of auxiliary ground rods. Another method for measuring earth resistance is the clamp-on method. This method uses a specialized clamp-on meter that measures the current flowing through the grounding electrode without disconnecting it from the system. The meter also injects a small voltage into the grounding electrode and measures the resulting current. The earth resistance is calculated based on the measured voltage and current. The clamp-on method is convenient because it does not require disconnecting the grounding electrode, but it may not be as accurate as the fall of potential method, especially in areas with high soil resistivity. In addition to measuring earth resistance, it's also important to measure ground impedance, particularly in systems with sensitive electronic equipment. Ground impedance measurements are typically performed using an impedance analyzer, which applies a range of frequencies to the grounding electrode and measures the resulting impedance at each frequency. The impedance analyzer can provide information about the resistive, inductive, and capacitive components of the ground impedance. This information can be used to identify potential problems with the grounding system, such as excessive inductance or capacitance, which can affect the performance of sensitive electronic equipment. When interpreting earth resistance and impedance measurements, it's important to consider the specific application and the relevant regulatory standards. The acceptable range of earth resistance and impedance may vary depending on the type of electrical system, the soil conditions, and the presence of nearby metallic objects. A qualified electrical engineer can help to interpret the measurements and determine whether the grounding system meets the required performance criteria. In addition to measurement, regular inspection and maintenance of grounding systems are essential to ensure their continued effectiveness. Grounding electrodes should be visually inspected for corrosion or damage, and connections should be checked for tightness. Soil treatment may be necessary periodically to maintain low earth resistance, especially in areas with dry or sandy soil. Proper documentation of grounding system measurements and maintenance activities is also important for tracking the performance of the system over time and identifying potential problems early on. In conclusion, earth resistance and impedance are critical parameters that affect the safety and performance of electrical systems. Accurate measurement, regular inspection, and proper maintenance of grounding systems are essential to ensure their continued effectiveness in protecting people and equipment from electrical hazards. The methods and techniques described here provide a foundation for understanding and managing earth resistance and impedance in various applications. By applying these principles and consulting with qualified professionals, you can create safe and reliable electrical systems that meet the needs of your specific situation.